Welcome to the 14th class of this course. Let me summarize what we did in the past few classes. We introduced the Legendre differential equation. Then we solved it, and so this is the general solution we got, which is a linear combination of two linearly independent solutions. These are y even L and y odd L. These are two independent, linearly independent solutions. And then after that, we truncated the series depending on the requirement that at x equals to plus minus 1, the series should be convergent. Okay. And then we got the Legendre polynomials, where L can take values like 0 and positive integers. Then we introduced Rodriguez formula, which can generate these Legendre polynomials. Okay. And generating function. This is also another method which can generate these Legendre polynomials. Okay. Good. So today what we will discuss is the orthogonality property of Legendre polynomials. Okay. So these Legendre polynomials, this p0, x, p1, x, p2, x, these are orthogonal to each other. But these are functions, right? So there is no sense of directionality here. So what do we mean by orthogonality? So let me start with what do we know, from our 10 plus 2 physics. What do we know by vectors? So let me start with very simple things like Cartesian vector in 3 dimension. Okay. So it's a vector in 3D. So in 3D there are three. So we can draw three orthogonal basis vectors. So these axes are x, y, z, x, y, z, and the basis vector along this x axis is basically I hat. Basis vector means the unit vector along the axis x, y, and z. Okay. So in 3D there will be three basis vectors. This is j hat and this is k hat, right? So in that case, any vector in this 3 dimension, any vector v in this 3 dimension, it can be written as a linear combination of this three basis vectors. So that is basically any vector in 3 dimension, it can be written as, let's say, v x I hat plus vy j hat plus vz k hat. Okay. And if there is another vector, for example u, which can also be written as linear combination of these linear combination of this basis vectors. Okay. So that is ux I hat plus uy j hat plus uz k hat. These are already known things, right? So this vx, vy, vz, these are the components of v along I. Okay. So what is vx? Vx is basically v dot I hat, right? So it's the projection of v. It's the projection of v along this x axis. Okay. Let's say if I project it, this will be vx. Here if I project it on y axis, so then this length will be vy. Okay. Similarly for ux, ey, and ez. So if the basis vectors are fixed, for example in this case I, j, k, okay, I hat, j hat, k hat, so in that case, to specify a particular vector, we need to fix three components in 3 dimension, right? So that means if the basis vectors are fixed, I can write this vector as like Vx, Vy, Vz also. So it just means like, so these components are separated by these commas. Okay, so it means like Vx I hat, Vy j hat, Vz k hat. So it means like the component on the x axis is Vx, v component on y axis is Vy, and component of z axis is Vz, right? And similarly this u can also be written as like ux comma uy comma uz, right? So these components, these are called the tuples. So in 3D there will be three tuples, okay? Vx, Vy and Vz. If I specify Vx, Vy and Vx, Vy and Vz, that means I am specifying the vectors. So the addition will be like, if I do u plus v, then it will be like ux plus Vx I hat plus uy plus Vy j hat plus uz, sorry, or I can write it Vz plus uz, same thing, Vz plus uz j hat, right? And this can also be written as, so if I want to write it in this form, okay, it will be like Vx plus ux, okay, this will be the first component, right? So the tuples will be like Vx plus ux. So this tuples will get added basically. So Vx will get added with ux, Vy will get added with uy. Okay, for example, for addition or subtraction, both cases, right? If I want to do a scalar multiplication, so if alpha is a scalar and I want to multiply it with v, then in this tuple form I can write it as alpha vx comma alpha vy comma alpha vz, right? And if I want to do dot product between v and u, in that case the dot product will be vx ux plus vy uy plus vz uz. So it's like multiplying this first tuple of v, that is vx, with first tuple of u, and then adding it with the multiplication of first tuple of first tuple of v, second tuple of v times second tuple of u, and so on. Okay, and if this is the dot product, this is how dot product is defined. Okay, and if this v dot u it becomes 0, then we say that okay, and v and u and v not is equals to 0 comma u not is equals to 0. In that case we say that v and u, they are orthogonal to each other. Okay. So this is what we know from 10+2 physics, right? So here orthogonality means like they have a angle of 90 degree in between them, they're perpendicular to each other. Okay, and normalization means, so normalization means normalization of, let's say, v, it means finding unit vector along v. I'm writing it as v cap or v hat, which is v vector divided by the mod of v, and mod of v is nothing but root under of v dot v. Okay, the dot product with itself, root of dot product with itself, that is nothing but v divided by vx square plus vy square plus vz square. So this is how we can normalize a vector. That means we can find a unit vector along that direction, right? Now what we will do, we will throw away this notion or this idea of directionality and magnitude from our mind, okay? And we will concentrate on the algebra only. So this is the algebra part, whatever we did here, and this is the kind of pictorial part, okay? Like we want to draw vectors, we want to see the angle between them and all, okay? We want to associate a direction and magnitude and all. But now what we will do is we will throw away all these properties of directionality and all, okay? So, and we will concentrate only on the algebra. So in this case, if I generalize things like generalization for n dimension, how do we do that? So in n dimension or higher than 3 dimension, we can't have any pictorial representation in our mind, right? We can only think up to 3D. So in that case, what we need to do is for n dimensional vectors, we need to concentrate on the algebra. We don't have any pictorial representations of these vectors. So if I concentrate on the algebra, so for n dimension there will be n bases, right? In 3 dimension there are 3 basis vectors like I, j, k, right? So for n dimension there will be n bases. There will be n perpendicular and unit vectors, okay? So let me call them, so n bases there will be so there will be n number of basis vectors. So instead of I, j, k, because then we will be run out of the alphabets, so let me define them like, so these are the basis vector set. It is like e1, e2, e3, comma dot 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 en. This is a set of basis vectors, for example. So in that case, any vector in n dimension that can be written as, so any vector v in n dimension can be written as linear combination of these basis vectors, right? So it can be written as, for example, v1 times e1 plus v2 times e2 plus v3 times e3 plus dot 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 plus vn times en, okay? And what is this vn, v1, v2, v3? These are the components of the vector v along those basis vectors. So basically vi means v dot ei, okay? And how the dot product is defined, that I will show you a little bit later, okay? So also I can write it as tuple form, right? It's like v1 comma v2 comma v3 comma dot 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 vn, okay? So in that case we will assume that this basis vector is already defined, it is already predefined, and we will only concentrate on the components, okay? So in that case, if there is another vector u in n dimension, for example, its components are u1, u2 comma dot 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 un, right? So then in that case v plus u, we will add it like that, so like this. So v1 plus, so first tuple will get added with the first one of u, right? u1 comma, so this will form, so v1 plus e1 will form the first tuple of v plus e, and v2. So the same algebra we are following, but we don't have any pictorial representation here because we are in n dimension now. So v3 dot 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 vn un. Similarly, the scalar multiplication that we will write as, for example, if I multiply it with alpha v, then we will write it as alpha v1 alpha v2 dot 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 alpha vn. Okay, and the dot product v dot u, that can be written as, so I will follow the same algebra basically. So algebra is saying that, okay, vx ux vy uy. Okay, so in that case, if I follow the same algebra, then v dot u will be v1 u1 plus v2 u2 plus v3 u3 plus dot dot dot. Okay, so the dot product will be there for n dimension, will be v1 u1 plus v2 u2 plus dot 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 plus vn u1. So this is how the dot product is defined for n dimensional Cartesian vectors. Okay, and if it is 0, if v dot u equals to 0, that means if this value is 0, then we will say then v and u are orthogonal. Okay, and we are assuming that assuming v not is equals to 0 and u not is equals to 0, right? But we are saying they are orthogonal, but there is no sense of directionality here. It is just the algebra. Okay, if this product, if this term, if that is 0, then we will say that, okay, they are orthogonal. Okay, we don't expect to see any angle between them that will be 90 degree something, because there is no such picture. Okay, and normalization is basically, let's say we want to normalize this vector v, that means we want to find out a unit vector along v, but there is no sense of directionality and all. Okay, so it is just the algebra, so it will be v divided by mod of v, which is nothing but v1 v2 v3 dot 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 vn divided by root under v1 square v2 square plus dot 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 vn square. And now this is a scalar, right? So this is a scalar, so then v we can write as so the first tuple of normalized v will be v1 divided by root under this v1 square plus v2 square plus dot 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 vn square. The second tuple will be v2 divided by the same term, dot dot dot, it will go like this, vn divided by the same term. Okay, this is how we will normalize, but we don't. So the algebra is basically we are mapping from 3 dimension to n dimension, but there is no sense of like directionality and all. Okay, so I think you must have heard about Fourier series, right? So okay, so let me talk about Fourier series a little bit later. So here we did is we took the idea of 3-dimensional Cartesian vectors, the idea of the algebra, not the directionality. So the idea of algebra we took from there, and then we generalized it for n-dimensional vectors. Okay, but these are still these Cartesian vectors. Okay, but what about functions? Here we are talking about Legendre polynomials. So these are the functions, and we want to show that they are orthogonal to each other. So in that case, how do you define the orthogonality? What do you mean by orthogonality? So before going into the orthogonality of Legendre polynomials, let me show you something else. Okay, so you must have heard about Fourier series, right? What it is? It says like, if you are given any function fx, okay, that follows certain conditions. Okay, there are certain conditions that those are called the Dirichlet conditions, but I will not explain them. If you want to know more about it, you should learn it separately. Okay, I think a lot of online contents are available in the internet. So any function fx that satisfies some conditions, it can be written as a0 by 2 plus sum over an cos of nx. Okay, and if fx is periodic, so if fx is periodic and we have a period of pi, okay, and if it's periodic and have a period of 2 pi, sorry, so in that case, which is like f of x plus 2 pi equals to fx. So for example, if fx is a, for example, this is, let's say, minus pi, this is pi, okay, this is 2 pi, so it's 3 pi, like that. So then fx, let's say fx is like that. This is fx, this is x-axis. So let's say if okay, so these kind of functions, so it has a period of this 2 pi from minus pi to pi, right? So in that case, fx can be written as like this. So n equals to 1 to infinity plus sum over n equals to 1 to infinity bn sine of nx. Okay, so this an bn, so these are the these are the coefficients of, or scalar coefficients of, this sine and cos functions. So these are the constant values. So if we fix a0, an, bn, in that case we are fixing the function fx, right? So here this cos nx, sin nx, and here there is 1, nothing, if there is nothing multiplied with it, that means there is 1 multiplied with it. So they are basically orthogonal bases if you are thinking in terms of vectors, for example. Okay, and here what you are saying is, so just as any vector in n dimension, for example v, it can be written as a linear combination of these basis vectors, okay, which is like, so basis vectors are e1, e2, e3, e4, dot dot dot, and any vector v that can be written as a linear combination of these basis vectors, that means v1 e1 plus v2 e2 plus v3 e3, but this v1 v2 v3, these are the scalar constants. Okay, and if I fix this v1 v2 v3, the v will be fixed, the vector will be fixed. Similar to, following the same algebra, this Fourier series is written considering this 1 cos nx and sin nx for n equals to 1, 2, 3, 4, 5, and so on. Those are the basis vectors, and this an, bn, a0, this an, bn, a0, those are this scalar coefficients. Okay, and here Fourier series, in Fourier series, it is claimed that any function following this Dirichlet conditions, they can be represented as a linear combination of those basis vectors. What are those basis vectors? Those are this 1 cos nx, sin nx. Okay, this is the same idea we used in case of Fourier series. So in Fourier series, how many bases are there? Like 1 is a basis, right? There are cos nx, sin nx, those are bases also, and n can take a value up to 1 to infinity, right? That means there are for each value of n, we will get 1 1 1, one basis, like cos x will be one basis, cos 2x will be another basis. So how many bases are possible there? There are infinite number of bases possible. So here, whenever we are talking about Fourier series, we basically in a infinite dimensional space, we have infinite number of basis vectors. In case of 3D, we had 3 basis vectors like I hat, j hat, k hat. But here in this function space, we have infinite number of basis vectors. So we are basically infinite dimension. We are in infinite dimension. But please do not try to have a pictorial notation, pictorial representation of it. You cannot have. It's basically the algebra. The algebra is looking the same basically, and that's why we are saying that okay, we are in an infinite dimensional space whenever we are talking about Fourier series. Okay, so in that case, we should have a notation about what do we mean by dot product, what do we mean by inner product in these functions, or in case of these functions. So the question is, how do we define the dot product or in the inner product? Okay, for functions. Okay. So for any functions a and b, ax and bx, or fx and gx, whatever you want to say, let me write as fx and gx. Those are generally used to denote functions. For any functions fx and gx, orthogonality, or any functions fx and gx, any functions fx and gx will be called orthogonal, if orthogonal in some specific range, in let's say a comma b, if the inner product, let me define it by I, from integration from a to b, f star x gx, okay, this star means complex conjugate, dx equals to 0. Okay, so this is defined as the dot product between two vectors, between two functions. So dot product is defined as, so dot product between fx and gx on a to b is defined as a to, sorry, there is no, this is no minus, a to b f star x gx dx, or a to b g star x fx dx. Okay, this is how the dot product is defined. Star is complex conjugate, and if the dot product is 0, if this integration a to b f star x gx is 0, then they are called orthogonal. So it's a new definition of dot product, and under this definition the orthogonality follows the same algebra, like the dot product becomes 0. That means we are calling it orthogonal, but there is no directionality here. Okay, it's just the same algebra they are following, subjected to a new definition of dot product. Okay, So let me give you some homework related to this new definition of dot product. Homework. Show that x square and sin x are orthogonal on -1 to 1. Okay, so that means what you need to show, you need to show that the inner product of x square and sin x. What do we mean by inner product? That is, in case of functions, it is x square star sin x from -1 to 1, and now x is a real quantity, right? -1 to 1 it is varying. So that means I can omit this star, because x star is x, right? But in general, if you are dealing with complex numbers, then this star should be included. Dx, what I need to show is basically show it equals to 0. Okay, so it's just a 10 plus 2 integration. Okay, 10 plus 2 level integration. Okay, now let me give you another homework, that is the functions fx and gx are orthogonal orthogonal on -a to a, this interval, if one of them is even function and the other one is odd function. Okay, so by even function, what I mean is basically, for example, let's assume that okay, fx is even function, you can take gx also, no problem. But I am, for the time being, let's say fx is the even one, so it means like f of minus x equals to fx. Okay, and for odd function it is defined as, so let's say gx is the odd one. Okay, and g of minus x will be minus of gx. Okay, this is the even and odd function, and what you need to show is basically fx is minus a to a. I'm assuming x is taking scalar values. Okay, they are scalar functions, so I'm omitting the star, or you can keep it, no problem. Star x gx equals to 0. You have to show it. Okay, using these properties, these two properties. Okay, let me give you some other homeworks. Show the following things. That is integration from minus pi to pi sine of mx cos of nx dx equals to 0. Okay, and here I am assuming that m comma n not is equals to 0. Okay, then this is number 1. Number 2, and what it will prove? It will prove that sine mx and cos nx, they are orthogonal. Okay, similarly, show that sine nx times sine mx dx equals to 0 if m not is equals to n. So what it will prove? It will prove that okay, for m not is equals to n, the sine nx and sine nx, these are orthogonal in this interval minus pi to pi. Okay, for example, sine x and sine 2x, those are orthogonal. Sine 3x, sine 4x, sine 5x, these all functions are orthogonal to each other. Okay, so number 3, minus pi to pi cos nx cos mx dx equals to 0 if m not is equal to n. Okay, what it will prove? It will prove that okay, cos mx and cos nx for m not is equals to n, cos mx and cos nx are orthogonal. Okay, and number 4 is minus pi to pi sine nx equals to 0 equals to minus pi to pi cos nx. Okay, assuming n not is equals to 0. Okay, so what this will prove? This will prove that okay, this sine nx, so if there is nothing means there is 1 times sine nx, right? So it will prove that this 1 constant and a constant function and a sine function and sine nx, these are orthogonal to each other in the interval of minus pi to pi. Okay, so basically what these, once you prove them, what you basically are proving is basically, in case of Fourier series, what we wrote is it's like a0 by 2 times 1 plus sum over of an cos of nx n equals to 1 to infinity plus sum over bn sine of nx n equals to 1 to infinity. Okay, that's how we wrote it. That's how we can expand any function. Okay, and here what we have showed is basically this cos nx, sin nx and 1 all are, and for different values of n, these are orthogonal. Okay, so what we showed is basically this 1 comma cos x comma sin x comma cos 2x comma sin 2x comma dot dot dot, these forms, these are orthogonal to each other. That means these will form orthogonal set, this will form a set of orthogonal basis vectors. Okay, and any function in let's say in function space. Okay, function space means I am talking about a vector space where the vectors are basically functions. That's how this function is treated here, right? This cos x, sin x are treated here. I am talking about orthogonality between them. That means those I am treating as vectors, but there is no notion of directionality. So these will form a set of orthogonal basis vectors in function space. Okay, and as a result, just like in Cartesian vectors, if we got in let's say in 3D, if we got any 3 orthogonal vectors, for example I hat, j hat, k hat, we can write any vector as a linear combination of them, and that's how here we are writing in Fourier series. Like we got this set of orthogonal vectors that we are treating as basis, and we are writing any function subjected to a Dirichlet condition. It can be written as a linear combination of these basis vectors. Okay, so that's what we did basically in Fourier series. And how many vectors, how many basis vectors are there? There are infinite number of vectors. So this n can go up to infinity, right? This cos 1x, cos 2x, cos 3x, cos 4x dot infinity, right? So there are infinite number of basis vectors here present in this function space. And here what that it means, like we are dealing in an infinite dimensional space. So whenever we are expanding a function in Fourier series, we are in an infinite dimensional vector space. Okay, that follows a similar algebra, but not the sense of directionality. So similarly, we will show that these Legendre polynomials they are also orthogonal to each other. And that means just like this 1 cos x sin x cos 2x sin 2x, they will also form a basis. And then we can, just like in Fourier series, we can write any functions as a linear combination of these Legendre polynomials. And that's basically what I tried to show you out as an exercise. So from the last class. So in the last class, I gave you some exercises. So that's the meaning of that. Okay. So we can write any functions as a linear combination of these Legendre polynomials. Once we prove that the Legendre polynomials, those are orthogonal to each other. Okay. So our claim is Legendre polynomials are orthogonal to each other. Okay, this is the claim. So Legendre polynomial means PLX. And how do we show them? The proof. What is the proof of that? So it means PLX, PMX, and orthogonal to each other on -1 to 1 in this interval. So -1 to 1 dx equals to 0. Right? So the inner product, that is -1 to 1 integration from -1 to 1 PLX, PMX dx. This is the inner product between PLX and PMX, and we will show that this inner product is 0. That means they are orthogonal. Okay, and assuming L not is equals to M. If L equals to will be equals to M, then the inner product will not be 0. Okay, so that will give you, that will be basically like the dot product with itself. So that will give you the length square basically of this, similar to like this length square of this Legendre polynomials, that we will be calling the norm. Okay, so that I will do in the next class. Let me show it that these Legendre polynomials are orthogonal in this class. Okay, and after that we will talk about the normalization of Legendre polynomials, and combined both this orthogonality and normalization, we will call them orthonormal. Okay, so that will be a topic of discussion for the next class. Okay, so let me show that. Okay, these PLX and PMX, these are indeed orthogonal. Okay, this integration is 0. To show that, we will start with the fact that PLX and PMX, these are solutions of this Legendre differential equations. Right? These are Legendre polynomials. So these will satisfy the Legendre differential equation. And what is Legendre differential equation? That is 1 minus x square y double dash x minus twice x y dash x plus L into L plus 1 yx equals to 0. And instead of yx, I can write it as PLX. Okay, this is how I will write. So I will write as PL. So in case of instead of y, I am writing PL. Okay? Because those are solutions we already know. So PL dash x. Okay, and it is PLX. Okay, and it can be written as ddx of 1 minus x square PL dash x plus L into L plus 1 PLX. If you do this differentiation, then you will basically get these two terms. So if you do ddx of PL dash x first, then you will get PL double dash x, And then if you do the differentiation of 1 minus x square, then you will get this minus 2x, where this PL dash x will be intact. Fine. Now the okay, now what we will do is we will multiply it with PMX. Okay. ddx 1 minus x square. We will multiply it with PMX 1 minus x square PL dash x plus L into L plus 1 PMX. I am assuming that this Legendre polynomials are real. Okay, so I am not talking about stars. So PM star or PL star. Good. Now let me call it equation 1. Now I will interchange this PLA, PL and PM. Okay, that I can do by interchanging. So because L and M, these are just arbitrary coefficients, right? Arbitrary indexes, not coefficients. Interchanging L and M, what we got is basically PLX ddx of 1 minus x square PM dash x plus L into L plus 1 PMX. Sorry, this is not L. I'm interchanging L with M, right? So it is M times M plus 1 PMX or PLX equals to 0. And as this is a multiplication between PLX and PMX, I can write it as PMX PLX. Let me call it equation 2. And now what I will do is like 1 minus 2, equation 1 minus equation 2, and then what we will get is nothing but this PMX ddx of 1 minus x square PL dash x, okay, minus this term, right, minus this term, which is PLX times ddx of 1 minus x square PM dash x, okay, plus L into L plus 1 minus M into M plus 1, and I will take this PM times PL, and here also PM times PL, so I can take that common. It is PMX PLX equals to 0. Okay. Now this term, it can be written as, this term can be written as ddx of 1 minus x square PMX P dash LX minus P LX P dash MX. Okay. Do it as a homework. Okay, you will see basically this ddx of this term is actually so if I put this outside PMX, right, then it will be just this term, right, and then there will be another term where this PM dash x and PL dash x both will be present, and those terms will be get cancelled when we do. So here if I do, then you will get two terms, one will be this term, another will be some other term, and that will get cancelled when we do ddx of this term. So once you do, you will understand. So do it as a homework. Okay? Show it. It's very easy. You will get 4 terms and 2 of them will get cancelled. Right. So, and the next term is basically plus, I'm writing it as it is, L into L plus 1 minus M into M plus 1 PMX PLX equals to 0. Okay. And now what we will do is basically we will integrate this whole thing from -1 to 1 dx. And if I integrate the right hand side, so if I integrate 0, it will be 0. I'm writing it as 0. And if I do the integration, what we will get is basically, so it is d dx, and here dx is multiplied, so it is d of the whole thing. So if I integrate it, we will get 1 minus x square pmx p dash lx minus plx p dash mx. Okay, and the limit, integration limit will be -1 to +1 plus I can write this L into L plus 1 times minus M into M plus 1 outside of the integral because it's a constant, right? And times integration -1 to 1 Pmx Plx dx equals to 0. Okay. And now if I put, okay, now notice one thing. If I put this limits, like I will put the upper limit, so it will be 1 minus 1, right? Then it will be 0 multiplied with this whole term. It will be 0 as long as this pmx and plx, or these terms basically whatever they are, like p dash lx, p dash mx, so these are not diverging at x equals to 1. In that case, this multiplication, like multiplication with 0 will be 0, right? So if I put the upper limit, then because of this term present here, so it will give me 0, and multiplied with whatever value, whatever finite value we will get here, the net value will be 0. If I put the lower limit, that is -1 also, then also because of this term it will be 0, right? Because whatever we are getting here, a finite value, whatever finite value we are getting here, if we multiply it with 0, then we will get basically 0. Okay, and it's also one importance that why we chose those solutions which are finite at or convergent at x equals to ±1. Okay? These properties will be helpful. I mean, these properties are a result of that choice. So then these whole term, it will be 0 because of this factor sitting here. Okay, so when we put the limits, and so basically what we are left with is L into L plus 1 minus M into M plus 1 times -1 to 1 Pmx Plx dx equals to 0. Okay, and now what we are assuming that M not is equals to L. If M equals to L, then this term will be 0, and there is no need to be this integral, there is no need that this integral should be 0. Okay, but if M not is equals to L, sorry, if L not is equals to M, in that case this term not is equals to 0. So in that case, this integration -1 to 1 Pmx Plx dx, it must be 0. Okay, and hence it is proved that for M not is equals to L, Pmx Plx dx or Pmx Plx, these are orthogonal, or the inner product between, dot product between Plx and Pmx is 0. Okay, so proved that Plx and Pmx are orthogonal. Okay, so let me give you some homeworks. based on that. So homework 1. Okay, one corollary of this orthogonality property is that integration -1 to 1 PLX times any polynomial of degree less than L times dx equals to 0. Okay, you can easily show if you have solved the homeworks I gave from the last class, because there we showed that, or I argued that any polynomial of degree less than L, this can be written as a linear combination of alpha n pnx, okay, where n is going from 0 to L minus 1. Any polynomial of degree, for example, any polynomial of degree n, let's say capital N, any polynomial of degree capital N can be written as this. So any polynomial of degree less than L, then they can be written as linear combination of this minus 1. Okay, so basically in this summation there will be terms like p0, so alpha 0 p0x plus dot 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 alpha up to alpha L minus 1 pl minus 1x. There will be no term like plx, right? And then if I multiply it with plx, so there will be plx p0x, plx p2x dot 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 plx pl minus 1x, and if I do the integration, then as plx is orthogonal to all other Legendre polynomials, then the integration will be basically 0 and the orthogonality follows from there. Okay, so based on these orthogonality properties and this corollary, let me give you some homeworks. -1 to 1, prove that, homework 1, prove that -1 to 1 plx p dash L minus 1x dx equals to 0. Okay, to prove it, you need to take the help of this corollary. Okay, because this p dash L minus 1x, what will be the it will be a polynomial, right? And what will be the degree of it? You can think about that. It will be less than L. It will be less than L minus 1 also. So, and then it will follow from the corollary that I showed. Okay, so number 2 is -1 to 1 plx dx equals to 0. Okay, so this proof of this is very easy. There is nothing here, means there is 1 multiplied with it. Okay, and here subject, it is conditioned upon that L not is equals to 1. Okay, L should be greater than equals to, sorry, L not is equals to 0. Okay, L is greater than 0. L is greater than 0. Okay, and this 1 I can write as p0 x, right? And if L not is equals to 0, then it follows from the orthogonality property. Okay, so the last homework is basically okay, not the last one. So use Rodriguez formula to show that p of L minus x equals to -1 whole to the power L of plx. Okay, while deriving the Legendre polynomials, we verified this property for some Legendre polynomials, right? p0, p1, p2, p3, but we have not proved it yet, but you can prove it using the Rodriguez formula. So it is basically showing that for even L, the plx's are even functions, and for odd L, the plx's are odd functions. and the last one is basically you need to show that P1x is orthogonal to PLX whole square on -1 to 1. Okay. So for that you need to use this property. So these are the homeworks. Do them, and in the next class I will talk about the how to normalize a Legendre polynomial. So that means like the inner product between two Legendre polynomials is defined as PLX PMX dx from -1 to 1. Okay, these Legendre polynomials are defined from -1 to 1. So from -1 to 1. So this is the definition of dot product between two Legendre polynomials, right? So basically then the norm of this PLX, it can be written following the same algebra for vectors, like for Cartesian vectors, directional Cartesian vectors, that it will be root under -1 to 1 PLX dx. Okay, right? So basically if you calculate PLX dx, you will see that it is not equals to 1. So that means dot product with itself for Legendre polynomials, it's not equals to 1. So that means this PLX for L equals to 0, 1, 2, 3, 4, these are not normalized. Okay, the dot product with itself, those are not 1. So it's analogous to unit vectors. So these are not unit vectors if I'm talking about vectors. Okay, so we need to normalize them. That's the basic idea. So we will normalize them, and then we will talk about Legendre series, just like the Fourier series. Okay, so in Fourier series what we did, so we defined this set of basis vectors, right? So these let me go here. Yeah, so we defined this set of basis vectors like 1 cos x, sin x, and in Fourier series what we did is we basically wrote a function which is subject to Dirichlet condition. It can be written as a linear combination of these basis vectors like 1 cos x, sin x, cos 2x. Okay, similarly here, so these basis vectors, why we are calling them basis vectors or basis functions rather, this 1 cos x, sin x, cos 2x, cosine 2x, because their inner product, which is defined like this, okay, defined like this, so their inner products are 0. Okay, and here what we showed just now is basically the inner product between PLX and PMX, any two different Legendre polynomials, 0. That means they are orthogonal. If you pick any two different Legendre polynomials, they are orthogonal. That means they can form a basis, and this L can go from 0 to infinity. So they can form a basis set, okay, a set of basis vectors with infinite number of basis vectors, right? So this set P0 x, P1 x dot 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 infinite number of Pix dot dot dot, okay, PLX dot dot dot. So and all of them are orthogonal to each other, right? So that means they can form infinite number of bases, and then any function can be written as a linear combination of these bases functions or basis vectors. So those will be called the Legendre series, just like Fourier series. Okay, so that's the idea, that those things will be discussed in the next class. Okay. So that's all for today. Bye.